So in the last activity, we saw the different responses that you could get from first order systems. So now it's worth taking a look at second order systems. These will be our kind of guiding systems throughout the entire course. And so let's go ahead and apply the same techniques specifically for the step response for the second order systems. So again, we're going to take the initial conditions to be 0, so that allows us to easily get rid of these terms that are part of both y double dot and y dot. So if I wanted to be correct, I really ought to have a1 multiplying sy minus y of 0, but then this guy goes to 0, and so we don't keep them. So now we're just left with s squared y, a1 sy, and a0 y is equal to Laplace transform of u. And so this is the thing that's different from our treatment of the homogeneous case. So our Laplace transform of our output y looks like this. And if we wanted to, we could go ahead and factor this into two terms, and we'll call the two poles P1 and P2. And because these are, there's a quadratic in the denominator, we know that the roots can either be both real or complex. And so there's a variety of different ways in which you could get these poles. And so whenever you get complex poles, remember they come as complex conjugate pairs. So the real part is the same and the imaginary part is opposite sign. So it's plus or minus IW. And so that's why when we create the pole zero diagram, you're always going to see complex conjugates appear like this. So they'll be symmetric about the real axis with the same real value. So that's why they're vertically stacked, and then either plus, so this is the sigma value, and this is plus omega, and this is minus omega. So this is when the real part is stable, this is when the real part is unstable, because now the real part's out here on the right half plane. With two real poles, they could either be so again, real poles won't be off of the imaginary axis, so they're not going to be up here or up here. They're just going to be on the real axis. So they both could be stable here, or they could both be unstable. They could have one stable and one unstable, like here. So there's a variety of different ways that the poles can come out of the system, and so that's obviously going to affect the way that the system behaves. So if we go ahead and plug in, if we're dealing with the step function, the step response, we're going to get the Laplace transform of the step function. That's 1 over s, and plug that in here. If we were to do that, that gives us this s factor down here. And when we do the partial fraction expansion, if you wanted to go through it all, these are the terms, and you'll go through a similar example in one of the homeworks for a slightly more complicated system. But ultimately, it's not super important what these coefficients are, kind of from a theoretical point of view. When you deal with a particular problem, it's going to be important, because these are going to be how much of each of these terms, each of these different modes you're going to have. But when we take the Laplace transform, you don't need those coefficients to see that you're going to have a constant term that comes from this 1 over s term, and then you get two exponentials. And so 2 points are interesting to make. One is the fact that we have this constant term. So it's just like in the first order case, you've got this extra constant term. So when we apply a force, essentially, and keep it on, and that's what the step response is, that it makes sense that you could have these exponential terms, but then you'd also have this kind of offset term. So that's due to this essentially force that's being turned on and held at a constant value. These exponentials, depending on what the poles are, what these values are, those could be different things. They could be exponential decay, they could be exponential growth, and then remember, in the context of complex poles, this exponential becomes a either growth or decay bit based on the real value, and then an oscillatory bit that's due to the distance away from the real axis. So the further these are away, so the closer they are in this case, In this case down here, the oscillation is relatively small. That omega is relatively small, so it's smaller frequency oscillation. Here, you've got larger frequency oscillation because these are further away from the real axis. Omega is bigger. So again, similarities with the first order case, but a few differences. Simply certainly the solution gets a little bit more complicated with a couple extra terms. And the potential of having two poles instead of one adds to interesting bits of the dynamics.